Hey, welcome back. In this video, we're going to continue the conversation about finding moments in center of masses. So far, we've tackled the discrete one-dimensional case and the discrete two-dimensional case. And just to review that two-dimensional case, because it'll be useful for the conversation we're about to have, we have these moments about the y-axis and the x-axis right here. And what those are the summations of these moments. For the y-axis, for about the y-axis, it's the moments with respect to the x values. For the x-axis, it's the moments with respect to the y's. And that's really important. Again, what this one is giving you, it's giving you, for this plane, the tendency to rotate about the y-axis, or in other words, it gives you the vertical axis of rotation. And then the vice versa for the x, it's giving you the tendency for this mass to rotate about the x-axis, or in other words, it's giving you the horizontal axis of rotation or of balance. And in this video, what we're going to do is expand on that. And as you might think, we're going to think about this instead of these discrete cases, we're going to think about these continuous or solid region objects. And this is where we're going to bring in the idea of integration. First up, I have here, we're going to talk about a flat plate, which we call a lamina, of uniform density P, meaning the shape is not uniform, but the density of the plate is uniform. And what we're going to look to do is to find the center of mass of this object. And importantly, we call this a centroid. So we have this lamina of uniform density. What we're going to do is attack the area on top of this plate. We'll call this region R. So what we're going to do then is we're going to superimpose this lamina onto the XY axis, just looking at this vertical face right here. A and B are going to give us the length of this object from this point of view right here. And importantly, again, because this has uniform density, we really can just look at this face. And so again, our goal is, given this, we want to be able to find this center of mass. We're going to use, again, exactly the same analysis with these moments. It's going to be a little bit more complicated because we have this fully continuous two-dimensional object. But at this point, I'm sure you have a very good idea where I'm going to start. The first thing I'm going to do is start splitting this up into n rectangles. The end goal is to describe it with n rectangles and then let the number of rectangles go to infinity. Let's specifically talk about the ith interval right here. So I'll describe this interval right here. This starts at x sub I minus 1 and x sub I. Then I'm going to choose the midpoint of this interval right here, and we'll label this xi bar. This will be our sample point for creating these rectangles, meaning this is really, these rectangles that we're looking at are like these midpoint approximation rectangles. And first things first, and this is really important, I'm going to use a symmetry principle to make this a little bit easier for me. The symmetry principle says if you have a region that is symmetric about a line, this can be a vertical, horizontal, or a slant line, it does not matter. But if the region is symmetrical about that line, then the centroid must lay on that line. And I won't prove that. If you think about that, it should be really clear, right? So if you had like let's just say something like a meter stick, right? So you have a 1 meter stick right there, and it's uniform across it. It's symmetric about the very middle of that. And so that line that cuts that meter stick in the middle must be where the centroid lies. So then for us, what that means is that the centroid must have an x value of this xi bar. That's really important. But so again, xi bar, I'm saying, is the midpoint of this ith interval. So I know that must be the x value. So if we're looking at the centroid here of this interval right here, I know the x value is xi bar. And then using the same logic, I have this rectangle here. I've identified that the centroid on this horizontally must be in the middle, but it's also the same conversation. It must be in the middle from the vertical standard of this rectangle. And so the height of this rectangle, as I've defined them, again, I'm using these xi bars as the heights, these midpoints. And so this height of this is 1/2 of the height of this rectangle, or 1/2 of f of xi bar. So the y value for this centroid, for this ith interval, would be this right here. So again, my goal at this point, what I'm trying to do are create these moments about the x and the y axes. What I need for that are these distances from the axes that I'll be using. For the moment about the y-axis, I use the x values. For the moment about the x-axis, I use the y values. That'll be important in 1 second. But then also I need to calculate these masses. So what I'm going to do for each of these centroids is calculate the mass. The mass of this rectangle right here is the area of this times its density, and our density is defined as rho right here. So I want to just label this then. So the mass of the ith rectangle is rho times its area, which is f of xi bar times delta x. And just to clarify that real fast, this is the area of the ith rectangle. This is the height. And then this is the width of this interval right here. I'm multiplying that area by its density to find the mass of this interval. All right, so then what I'm going to do is identify the moments about the x-axis of this region and the moments of the y-axis about this region right here. And again, I have this over here just to hopefully make it obvious what we're doing and how it's exactly the same. What I'm going to do, so I'm going to find the moment about the y-axis of this ith region right here. And what I'm going to do is do exactly the same thing I did with the discrete 2D system, is multiply the mass, which is identified as this right here, times the xi, or the x position, the x value, which is xi bar in this case. And then for the moment about the x-axis, I'll have exactly the same thing. The only difference is I'm going to multiply this mass by the y value. So let me write this out here. I have the mass here, and now times the y value, which is 1/2 f of xi bar. And I know at this point there's a lot of notation going on right here. This is, again, depending on how much physics you've had in your past, how intense this is. Again, this rho is just a constant value with uniform density. So it's the uniform density of this lamina. What I first did was identify the centroid of a representative rectangle in this interval right here. The mass of that interval is simply the area of that rectangle times that density. And then the moments about the y and the x-axis are then the mass, which is exactly this in both of them, and then multiplied by, then let's just say this is important. For the y, this x bar I is, I'm multiplying it by the distance of this object to the y-axis. That's what this is right here. So this is xi bar. That's the distance to the y-axis here from the centroid of this region. And in the same way, for the moments about the x-axis, I'm multiplying this mass times the distance to the x-axis, and in this case, that's this right here. All right, let's jump into the good stuff. And what I've done, as always, is identified the interesting information I'm looking at for a representative interval. Given n intervals, this delta x is determined by the number of n. If I then let n go to infinity and sum up each of these. So if you remember, the moments of the system is when you sum up each of these moments for these individual parts. So if I sum to find the moment with respect to the y-axis for the entire system here, I'm summing this again as n goes to infinity. This statement right here gives me the fact that my moment about the y-axis would be the integral from a to b of rho times x f of x dx. And the same way for my moment about x, when I let n go into infinity, I sum up each of these moments. I get my moment about the x-axis to be the integral from a to b of rho times 1/2 f of x squared dx. And then before I generalize this process, I just want to make it really clear how I got these right here. I feel like maybe I jumped pretty quick through that. So first of all, again, for each region, the moment about the y-axis is the mass times this x value. Then in this case right here, all I did was rearrange my information to get it here. I moved this x bar I or xi bar here in between this because it's all just multiplication. And then in this case, this is the one that maybe isn't so obvious. What I did was multiplied these function values together. I have two factors of this xi bar or f of xi bar. Multiplied those together to get f of xi bar squared, and then I get that factor of 1/2. And again, the 1/2 in this case comes from the fact that I was looking halfway up this rectangle for that height. So then if you remember back to the discrete case, how we found this centroid or the center of mass for our system was to take these moments with respect to the y-axis and the x-axis and divided them by the masses to find those x and y values. It's exactly the same thing here. So the only thing that we might be thinking at this point is, well, how do we find the mass of this object? And actually, it's beautifully easy given the fact that we have a uniform density. All we need to do is multiply that uniform density by the area under this curve, which represents this face right here. And we can find that just by computing the integral of this function that defines this or bounds this region right here over the definite integral from a to b. So to finish this up, we have the mass of this region is simply the integral from a to b of our function f of x dx multiplied by rho. So then to clean things up and just to make it nice, neat for your notes right here, here I've generalized everything we just showed. So first of all, we're talking about a region. It's bounded by a continuous function, the x-axis, and these lines a and b. So exactly the picture we just had. Rho denotes the uniform density. We calculate the mass by multiplying the density times the area under that curve. And again, in the other cases, I wrote rho inside the integral, but it's simply a constant density, so I can pull that out, which I've done in each of these cases right here. The moments, as we've defined, are the moment with respect to the y-axis is rho times x, the integral from a to b of x times f of x. And then for the moment about x, we have rho times 1/2 the function squared inside the definite integral from a to b. Then when we're looking for the centroid, so for the center of mass for this lamina, what we do is for x bar, we take this moment with respect or about the y-axis divided by the mass, and for the y, we do the moment about the x-axis divided by the mass. So the obvious application of this right here is where we have a lamina that's defined in exactly this same way. There's actually one really cool other application that we can do is that since we have this now continuous two-dimensional object, well, two-dimensional with a little bit of thickness right there. But let's look back at this real fast. I want to describe what we're going to do or can do if we have non-uniform density. Because again, importantly, is this uniform density? So let's get a lamina here as described by this function here. So we have this from a to b. So importantly, all along this surface right here, I have uniform density. But if I were to choose any one of these spots, let's just say, let's call this xi for whatever. I'm not going to split this into rectangles. But I want to think about this. If I instead took this and I wanted to smash this function down, but keep the actual mass at any one point. And actually, this couldn't just be an instantaneous point. It'd have to have a little thickness for this to make sense. But again, I'm just going to kind of walk through this concept that you'll see what happens. If I did this and I smashed this down to keep at each x value the exact same mass, what I would get is this object, and we call this a rod, that would sit here on the x-axis that now would not have uniform density. What that allows us to do then is think about if someone gives us a rod that has non-uniform density right here, we can extrapolate it using this same thought right here. So again, this case had uniform density across this. If we smash it down, it has non-uniform density. The changes in density are described by those function values right there. So if someone gives us a density function for this one-dimensional object, or mostly one-dimensional object, let's say, then we can let the p of x equal the f of x in our function definition over here. Again, to clarify what I'm stating right here, and there's other ways to prove the statement that we're going to use, and I'll use this idea in 1 second right here. But the idea is if we've proven this for a uniform density lamina that has 2 dimensions right there, but then we just smash this directly along these x values right here, take all of this function height right here, this this mass on this xi right here and smash it down, we will then, if we didn't have a constant function, we'll then not have uniform density. That non-uniform density is described by the function heights right here. So in general then, if somebody gives us a non-uniform density described by some function on the interval, all we need to do is take that density function and replace it in the f of x in here with that density function. All right, so in this first example, I am looking for the center of mass for one of these rods that has non-uniform density. And again, I'm thinking of this non-uniform density function as my second dimension right here, of this f of x function described over here on the interval from 0 to pi over 2. So what I'm going to do in this case, again, I'm only going to be looking for one dimension just along the x-axis here. So I'm going to find x bar. And so x bar is the moment about the y-axis divided by the mass. And so to remind ourselves of those formulas, so the moment about the y-axis is this right here, and here is the mass. So I'm going to be dividing these from each other. One important thing is actually the rows on the outside here will cancel because they're just a factor outside of these integrals. And that's important here because it would be awkward if I had rho described in two ways here. And so what this will become, I'll just write this generally first. This will end up being, for this rod, from a to b of x f of x dx over the integral from a to b of f of x dx. Then as stated in this case, this f of x function aren't these height values. It's actually this density right here. And I have my bounds from 0 to pi over 2. So let's just throw that all in. So I have from 0 to pi over 2 of x times the cosine of x dx. And then down here, I just have the integral from 0 to pi over 2 of the cosine of x dx. The numerator, this is going to take a little bit of work. This was going to be integration by parts because of this factor of x out here. The indefinite integral of cosine is super easy. So let me attack this separately first, and then I'll go and I'll attack this and throw it all together. So if I'm going to calculate the integral from 0 to pi over 2 of x cosine of x dx, I'm going to use integration by parts. The u in this case is going to be the x because of liate. So u equals x, du then equals dx. And then that means that dv must be this cosine of x dx. Give me that the v function must be sine of x. So this ain't going to be too bad at all. When I plug that in, what I get then is a uv, so x sine of x, can't forget that I'm evaluating this from 0 to pi over 2, minus the integral of v du. So in this case right here, du doesn't add anything else, just sine of x. So this is not going to be too bad. 0 pi over 2 dx. And so then this is already integrated. The integral of sine, it's always in my head, always I go backwards. This gives me negative cosine, because that's what you have to differentiate to get to sine. And so negative cosine is what comes out from this. I got this negative here, and so I'll cancel that to get x sine of x plus the cosine of x, then evaluated from pi over 2, or from 0 to pi over 2. And then just to save myself a little space, I'm not going to write out all of those steps here, but I'll walk it through. When I plug into pi over 2 into this right here, so the cosine, this is just 0, so that doesn't do anything. When I plug pi over 2 in here, I get pi over 2 times the sine of pi over 2. The sine of pi over 2 is 1, so this actually outputs pi over 2 from that term on the top of the bounds here. When I plug in a 0, well, that's 0 times whatever. Who cares? Actually, they're both 0, but 0 times anything is 0. And then the cosine of 0 is 1. So I'm subtracting that value. So I get pi over 2 minus 1. So that was then the numerator. The denominator is going to be straightforward. So we'll just calculate that. That is the integral from 0 to pi over 2 of the cosine of x dx. And this is just the sine of x, which we're going to evaluate from pi over 2 to 0. At pi over 2, we get a 1. At 0, we get 0. So it's 1 minus 0. This gives us out 1. And this is about as well organized as I was thinking I could do, given my limited space with keeping all of this here at this time. But just to clarify, I've evaluated this and got pi over 2 minus 1 for this numerator value, that definite integral. On the bottom, I get just 1. So the center of mass here, this x bar, would be the pi over 2 minus 1 over 1, which obviously simplifies into pi over 2 minus 1. So again, just to review that before we move forward with another example, we found the center of mass in this case. We actually don't have a lamina, but we have a rod that's non-uniform density. So then our second dimension, instead of being like this height or this vertical change, we're going to use this density function as our second dimension. And so in finding x bar, that's all that we can find in this case. We don't have any change in y right here. We're just going along the x-axis with this non-uniform density. We divide the moment about the y-axis, divided by the mass. When we do that, this rho value, that's the uniform density of this original setup right here, gets canceled. That's nice for many reasons, just makes things a little bit easier to compute, but also it doesn't get awkward then when dealing with this non-uniform rho right here that actually varies over the interval. But we plug those in there, again, canceling the rows, and calculate each of these integrals right here, which I did, and I suggest you do is I do them separately, and then I divide them from each other. And I found then on this interval from 0 to pi over 2, the center of mass, or the centroid, is at pi over 2 minus 1. Let's now do an example with an actual lamina that will compute using this information right here. All right, in this example, we're being asked to find the centroid of a semicircular plate with uniform density and radius r. So in this case, first of all, I just want to impose this on an xy axis so I feel somewhat comfortable with this. This is going to be a half circle. So r is the radius. Let's see if I can get this about as symmetric as I can right here. That looks pretty close. And can I get the same height? Good enough. All right. So if I'm looking for this semicircular plate right here. Does that kind of look circular? Almost. Nice. Okay, with this region right here, and the work that I'm going to do is to find the centroid of that object. First things first, probably pretty obviously, is I want to figure out my bounds, my interval AB, and the function. And I won't go through all the work, but I'm sure you've seen this before. So this function right here, well, this is based on a circle being x squared plus y squared equals r squared, right? I'm looking for the top half in this case of such a circle. So that would be y equals, or I'm going to write it as f of x, equals the square root of r squared minus x squared. And again, just to write on the side here, if you're kind of lost with where that came from, that comes from this formula right here, solved for y. You get a top and a bottom. I'm just looking at the positive version of it right here. So let's go through these steps right here. The first thing I want to do is to find the mass. So the mass is, m will be rho, which is this uniform density. And now my bounds, I threw them in here, but just to make it clear right here, is from negative r to r, given this radius of r, of this right here. And this is where things might get kind of interesting, because I would need to use a trig substitution in order to calculate this integral. But the beautiful thing that I'm going to do is say, hey, I got this formula from knowing it's a semicircle. I actually know the area of a semicircle. It's half the area of a circle, which is equivalent to this, because again, this integral is just describing this area. There's no reason to do all that work if I already know the answer. So the mass of this region right here, this lamina, would be rho times 1/2 pi r squared. And then for me, I actually don't calculate the moments and then find the centroid separately. I always do that at the same time. But there actually is one really beautiful trick that we can use right here. And it's that symmetry principle that we had a second ago when we were describing this concept right here. And what that said is, if you have a region that's symmetric about a line, then you know for sure the centroid must lie on that line. And if we look at it right here, we know for sure that this object, this circular, semicircular object, is symmetric about the y-axis, which means our centroid must land on the y-axis, or in other words, x bar must be 0. Importantly, as you see here, that I've used two different tricks. One to find the area, or this integral using an area argument, and then here using the symmetry principle. You won't always be able to use these, but I wanted to model these and say, keep an eye out for these because you can make some of your steps a heck of a lot easier when you're doing this. But again, all I'm saying here is because this region is symmetrical about the y-axis, that my centroid, I'm not exactly sure where it's at, but it must show up on this y-axis, which means the x value of that centroid has to be 0. So then last thing that we need to do is calculate this y bar. So I'll set it up here. This y bar is the moment about the x-axis divided by the mass. We know the mass already, which is nice. The moment about the x-axis is calculated by this rho. Then from a, the indefinite integral from a to b of 1/2 times f of x squared dx all over this mass, which is rho times 1/2 times pi r squared. And I'm gonna have to do the work of calculating this. So again, f of x in our case is this function right here, the square root of r squared minus x squared. And just to make things a bit nice here, clean things up before I get going here, is actually the rows here can cancel. And then actually I can move this constant of 1/2 out and cancel that with the 1/2 here. So I just get pi r squared in the bottom, and I need to do the work of calculating this. I can now get rid of this because I've used all the information, and let's finish this problem up. All right, so we've got the rows and those 1/2s canceled out. So what I got is y bar equals this integral on top here. So from a to b is from negative r to r of the square root of r squared minus x squared, but that is squared, which by the way is going to work out really nice for this example right here, squaring that square root. And then the bottom, we get pi r squared. Just want to make a note right here too, that I could do, but I'm not going to do just because I want to go through all of the work with this integral right here. I actually, because this function right here is even, it's symmetric about this y-axis, like we just said right here to find this x bar point, I actually could go from 0 to r times 2. If you remember that from those properties of integrals way back, I could do that. It really won't save us too much time in this case right here. So I'm just going to again focus on that integral on top. Let's calculate that, and then we'll divide it by this pi over r squared to get our y bar. So this right here, those squares cancel, and so I get the integral from negative r to r of r squared minus x squared dx, which then integrating this is just a constant value term right here, so this becomes r squared x minus, and this gives us, we get x cubed over 3, and we're going to evaluate that from negative r to r. And then evaluating this at r, I get r times r squared is r cubed. R plugged in here gives me, I'll write this as a 1/3 r cubed. And then plugging in the negative r, this will be a negative r cubed. Minus, when I plug in a negative r here, the negative does make it out because of the odd exponent. So I'll get a plus 1/3 r cubed again. And then instead of rewriting it, I'll just distribute this negative here. That becomes a plus. This becomes a minus. So a plus r cubed minus a 1/3 r. So when I get this together, I get 2r cubed minus 2/3 r cubed, just to clean it up a little, make it a little bit easier. I can think of the 2 as 6/3. So 6/3 minus 2/3 gives me 4/3 r cubed. And then that's it. Basically, we're on the home stretch. We have that y bar then equals, this is the evaluation of this definite integral. So we have 4/3 r cubed. We're dividing that by this pi r squared. And so when we do this, I'm going to get left with 1r up there. And so how I could write this nicely would be leave the 4 up there with the r, and bring that 3 down here with the pi. And then we've done it. We've found our centroid for this lamina, which is a semicircular plate with radius r. We know the x value, which was easy. That was nice. It's at 0 because it has to be on the y-axis. And then we know our y value here is 4r over 3 pi. Last thoughts being, if you didn't see this use of the symmetry principle when you were doing this, it wouldn't have been that crazy, but what you would have found is that when you did the moment about the y-axis, you would have gotten 0, which then 0 divided by the mass would have gotten you x bar equals 0, so it wouldn't have been a ton of more work than what we did to find that right there. And this is a moment just to say this. I think this might help clarify that moment of the y-axis. Like, why does it have to do with the x values? So this value, or the moment about the y-axis being 0, means that your region is perfectly symmetrical about the y-axis. Therefore, the y-axis is the vertical point of balance of this plate. It's always hard to think from your place where you're at how intense this feels. But remember, go back to that box that I had up here for most of the lecture. That's really the saving grace. It just gives you those things. First, how to calculate mass, which is simply rho times your function value over on your bounds from A to B. And then we have the moment about the y-axis and a moment about the x-axis. We use those to find x bar and y bar. Once you've found both of those independently, then you're able to identify your centroid, which is the center of mass of this object.